Hello and welcome. My name is Aidan Boyd, and today I'm going to talk about a recent piece of work called CYBORG, Blending Human Saliency into the Loss Improves Deep Learning. I would love to be there with you guys presenting this in person, but unfortunately I couldn't make it, so that's why I'm doing this recording, talking about a recent piece of work from our lab. So this is the final part of today's tutorial. Should be about 50 minutes long. You've previously heard from Dr. Bowyer, Dr. Moreira, and Dr. Czajka, who talked about more so the iris recognition and the iris PAD side of it. But all of it is about incorporating human intelligence. And finally, it's going to be rounded out by this talk, where I'm going to talk about this recent piece of work coming out of our lab. So the outline for today's tutorial is as follows. I'm going to first of all talk about the motivation and how we got to this proposed piece of work from previous work. I'm going to talk about how we collected some data for this work and how we use this data to build human saliency maps. I'm also going to talk about the effect of this annotation data in terms of human performance compared to a previous work. I'm going to talk about the overall proposal of this paper, which is CYBORG loss, our experimental setup, and then the results and conclusions from this work. So, as you saw presented by Dr. Bowyer, in a previous work, we applied this human saliency concept or the acquisition of human intelligence in terms of where they deem to be salient. We applied it to iris PAD previously, where we asked individuals to identify the nature of an iris image as to whether it's an attack image or whether it's a live iris. And then what we did is we created what's called a human saliency map, which can be seen in the second component in the black and white in the bottom right. That's a human saliency map. We see the heat map representation where darker and red colors correspond to more densely annotated regions, and the blue regions correspond to sparsely annotated or unannotated regions. And what we did is we obviously, as you heard, blurred out inversely proportionally to the amount of annotations in that region. So the unannotated regions will be heavily blurred, and the most densely annotated regions will be left unaltered. And the idea for this was to simply just remove the information in an image that humans deem not useful in order to guide the network towards learning the human-defined salient regions. However, in this work, it's more so the suppression of human-defined not useful information because we're actually physically removing from the image unimportant regions through Gaussian blur. However, we want to discover in this work whether we can use this human saliency as supplemental material to the network. So we're not removing anything, we're just adding supplementary information. And this would hopefully help the network in that we're not forcing it to look at specific regions, we're supplying extra information and it can use this extra information or not, but the full unaltered image is being passed through the network. So the way that we do this is by developing a new loss function where we directly incorporate the human saliency information into the loss. And whereas previously we did iris presentation attack detection, we decided that we were going to switch the domain for this work, and we switched to open-set synthetic face detection. So synthetic face detection is deciphering the nature of face images as to whether they are genuinely real faces, like actual images of real existing humans, or whether they are false identities or fake images, so generated by either a GAN architecture or some sort of face stitching method, but this person does not exist. So that's a synthetic identity. So we're trying to detect that because it's now becoming in popular on popular social media and stuff, we see a lot of this fake identity leak in there. And we want to be able to be robust to that. We want to be able to decipher the nature of the face images so that people aren't caught by fraud or, you know, misleading fake images for there's many reasons why you want to catch something like this. So to do this, we collected a new data set. And the way we did that is we developed an online tool. And this is a screenshot from that online tool right here. And we asked 363 individuals from Amazon's Mechanical Turk to complete this survey, which consists of 30 pairs like the one on the screen right now. So each person was provided 30 pairs of images. And there are 1,000 total pairs, and each pair consists of one real image and one synthetically generated identity. So the real images are from a data set of actual people from the University of Notre Dame, collected by Dr. Bowyer and this team. And the fake images, or the synthetic images, come from two sources. The first, SREFI, S-R-E-F-I, is a face stitching approach to synthetic identity generation, and that is also out of the University of Notre Dame. The second, and probably known to a lot more people here, is StyleGAN2. And StyleGAN2 uses a GAN, generative adversarial network architecture, to generate false identities. And what we did is we downloaded 500 of those from thispersondoesnotexist.com. So that's a website that you can go to now and see some of these crazy fake identities there. They're super realistic. But in general, what we found is that with these super realistic faces, a lot of the time there is something in that image that gives it away. So whether it's like an elephant ear or like something weird going on with the teeth or the earrings, or maybe there's something with the glasses, a lot of the times, and even with SREFI as well, a lot of the times there is something in the image that would give away its nature. But if you just look at it quickly, you might not notice it. But if you really study the image, you can figure this out. So we wanted to see if humans could find these and correctly classify the nature of these images. So what we did is we asked questions such as the one here, where it's, which of the two images is a fake face? And for those of you familiar with SREFI, you would know that the one on the right here is the fake image. And the reason is there's a kind of an oddity around the eyes here and potentially along the jawline that would give away the nature of this image. So if I was doing this data collection, I would say the right image is the fake face. But the way that this data collection worked is this question changed for the same pair for different people, where sometimes it'll ask which is the fake face, and sometimes it'll ask which of the two images is the real face. And the reason for that is we don't want people or subjects to focus entirely on either fake features or real features. We want them to look at both of them and make a more generalized feature selection, having context of both. So you're given randomly assigned questions which ask which is the real or which is the fake. Here's another example which could be a little bit more difficult, as this is one of the images from StyleGAN2. As I said, in each pair, there is one real image and one synthetic image. So this one is a little bit more difficult, but if you're familiar with GAN architectures, you can see that this is the fake face, but that's pretty difficult. So someone that's not familiar with these false identities, this is a tough question. So maybe this one will be a little bit more difficult. Anyways, once the users, the subjects, select which image answers the question in their opinion, i.e. which is either the real or the fake face, we then ask them to, using their mouse and clicking and drawing on the image, annotate which regions support that decision. So simply they click on the answer to the question. So for this case, which is a fake image? I think it's the one on the right. So I click right image, and then I draw on the regions that make me think that. So in this case, this person decided that the eyes gave it away, the upper lip, and some of the jawline. There's artifacts there visible that led them to the decision that this image on the right is the fake. So looking at the comparison now, so the main starting point from this work is we wanted to see if we made people do this annotation, does human performance improve? So what we did is we started with a previous work out of Notre Dame by Dr. Bingyu Shen. And basically what they did was they collected these pairs. They generated the pairs and the questions, whether it's real or fake, and then presented them to mTurk users in the same way we did. This is a previous work, and they just said which is the real or fake, and then it was left image or right image, but there was no annotation. So it was two choice forced answer. And what we did in our work is we went one step further, where we copied the 1,000 pairs that they used in their work exactly, as well as the exact same questions that they asked their users. So we replicated their experiment exactly, except we added one extra step in that the users had to annotate the supporting regions. So we basically just copied their work with the addition of forced annotation. So without the annotation, the two choice forced answer, we see that the median is 50%. So what we see is the number of pairs and the pair accuracy. So say if a pair was annotated 10 times, what is the accuracy on that pair? If it's 5 people got it right and 5 people got it wrong, it'll be 50%. If everyone got it right, it'll be 100%. So it's that pair out of the 1,000 of them, the accuracy on that pair. So in their work, in the previous work, they concluded that humans perform with almost random chance in this task. So it's a really difficult task, actually. And also what they discover is that there's no difference between Srefi and StyleGAN, really, no significant difference in the difficulty. Both of them are kind of a normal distribution around 50%. However, once we added the addition of forced annotations, the median pair accuracy increased significantly to 69.2%. So nearly 70% now of the pairs are now being classified at almost 70% accuracy. And the median also increases by about 12%. Additionally, what we see is two distributions where we see that the StyleGAN images, which we previously mentioned are quite difficult to determine, actually are much harder than the Srefi images, which are the blue bars. So yeah, we can see clearly from this graph that although the accuracy went up, we see that this StyleGAN or the GAN generated images are much more difficult to humans. And we see a lot of pairs with 20, 30% accuracy, meaning that the people that are doing these annotations are getting quite confused by these hyper-realistic identities generated by StyleGAN 2. So we thought this was a cool discovery that, I mean, maybe it was obvious, but it's quantitatively, we can prove now that the addition of forced annotation increases the accuracy of human subjects online. So that was a nice finding initially. So now that we have these annotations, we then keep only the ones that correspond to correct classifications. Because we're trying to build a deepfake, a synthetic face detector that classifies correctly, we hypothesize that we just want to keep the correct classifications because we want the annotations that correspond to correct classifications themselves. So here we have an example. of an image on the left, a fake image generated by Srefi, and 8 correct classifications in B here. So we have 8 different users that annotated this correctly, and this is what they deem to be the salient regions. Then what we do is we combine them, we stack them all on top of each other, we just add them all together, and we add a Gaussian blur over that to smooth the edges between the areas of different annotation density, so we're not introducing edges in the actual saliency map, and we get what's called the human saliency map. Similarly, into the iris PAD work, we're again creating these human saliency maps, as can be seen in C. And D, similarly to in the figure on the first slide, we have a heat map representation of that. So here we have this sample on the left with the annotations overlaid, and we see that the people in general, the most densely annotated regions is the eyes, the nose, the mouth, and then a little bit less so the ears, and then one person thought the chin. So yeah, the eyes and the mouth seem to be the most important regions for determining the nature of this image in this example. So we get these human saliency maps for every image that has correct classifications. We generate these human saliency maps. Here are some more examples of images with some human annotations. So yeah, here is basically 3 examples of fake images with correct classifications, and as well as the heat map representations of the human saliency maps. So one thing that can be noticed immediately from this is that the eyes, the nose, and the mouth seem to be very important for humans in determining the nature of synthetic faces. In all 3 examples here, the eyes are pretty densely annotated. And as well, in one of them, the mouth is very important, as well as, and then the one on the very right, we have the nose is important and the ears. So the important facial features that you would think of, like the eyes, nose, mouth, ears, those are what people are using. It's not really the forehead or the hair per se. In general, people are looking at the eyes, the nose, and the mouth to make these determinations. So furthering on from that, we make our own new loss function. With this human saliency information, we propose CYBORG loss. And what CYBORG loss is a way of incorporating these human saliency maps into a loss function while maintaining the classification element. So CYBORG loss consists of 2 parts. The first is the human saliency loss, which I'll explain in a moment. And the second is the regular classification loss, the categorical cross entropy. So basically what we're trying to do is add another component in this human saliency loss to the traditional training, which is just classification loss, in an attempt to guide the network towards human salient features. And the way we do this is using the class activation mapping mechanism, CAM. For each batch, we probe the network about where it's currently looking using class activation mapping. As you can see in this example here, this is where the network deems is important using a CAM in this image, but this up here is where humans think is important, as defined by the data collection. And what we do is we calculate the distance between the human saliency map and the class activation map from the network. And we do the mean squared error loss between those. And in doing that, we're penalizing the network when it's looking at something completely different than humans. We want it to look at the same things as humans, but that's not the only thing we're forcing it to do. We're also, because of this classification loss, we're getting it to look at the human defined salient regions and also to classify it correctly. So given these human defined salient features, we want you to classify. That was the logic behind the development of this loss function. Can you become more aware of human features? as well as classifying it correctly. So here's an example of what I mean by that. Here we have an input real face on the left. And in the middle, we have the correct classifications from the data collection, the human saliency map, the heat map, similar to what we had a couple of slides ago where we had 3 examples. And then on the right, we have the class activation mapping from the network. So we can see that the humans are looking at the eyes and the mouth pretty closely, but the network is looking somewhere at the chin, a little bit this person's left eye, but mostly the chin. So clearly there's a discrepancy here, and we want to penalize this. We want the network to move closer to the human saliency map. So in this case, we would apply a penalty based on the mean squared error loss between this class activation map and this human saliency map. And that's the loss, the human saliency component of the loss. Similarly, for fake samples, in this case, for this fake image, the eyes were very densely annotated also. So humans deemed the eyes to be quite important for classification in this case, as well as a little bit the nose. However, the network deemed somewhere lower chin, the jawline, the chin, the neck to be important. So again, a big discrepancy here. We don't want that. We want the network to look at human defined regions and also classify correctly. So this is where the idea of CYBORG came up. We're trying to guide the network towards human defined saliency while also maintaining classification performance. So the experimental performance for this work is we started with the training data, which is all images from the 1,000 pairs. So obviously 1,000 pairs is 2,000 images that have correct classifications associated with them. And this resulted in 919 authentic real faces with correct annotations and 902 synthetic images, fake faces with correct classifications. The validation data consists of 10,000 real images from the same source as the authentics within the 1,000 pairs we collected in the training data. Obviously different images, but from the same source. And then an additional 5,000 SREFI generated images, SREFI, and 5,000 StyleGAN2 images. So the validation set is 20,000 images from the exact same sources and the same compositions as in the training data. So it's kind of closed set, I would say, in terms of training and validation. Obviously, there's no overlap in the images, but they're from the same sources. And we want to evaluate this in 2 main settings and 1 additional setting, so 3 settings. The first one is the traditional approach of just classification loss only. So just categorical cross entropy. We only care that the network is classifying these images correctly. So that is kind of like the baseline, the traditional approach. The second is we replace the classification only with CYBORG, which is the combination of the human saliency loss component and the same classification loss. So it's now 2 losses within 1, and we call that CYBORG. And we train in the exact same way with the exact same data. We train in the exact same way, so we can compare the difference between the performance on the test set of these 2 approaches. Going on from that then, once we have the fair comparison using the same images, only just a different loss, we then increase the size of the training set by 7x and train on that. And the idea is to try to gauge just how much of a performance gain we can see by CYBORG. So this is comparing how much difference does adding these human saliency maps make versus just increasing the size of the data set. So in one case, we have limited data and we're getting more value out of it. versus the traditional, how do we get more performance, just add more data approach. That's what we're kind of studying here. So here's just one example from each of the data sources. This FRGC subset is collected at the University of Notre Dame, and that's what we used for training and validation as the authentic, real, genuine samples. For the training and validation, we used SREFI, as I mentioned before, and also StyleGAN2. So these are the two synthetic images. Okay, now for the test set, we have two authentic sources. We have Flickr Faces HQ and Celeb HQ. And then we have 5 additional, we have 6 total testing GANs that generate synthetic faces. So StyleGAN2 appears in the training and validation, but we also generate an additional 100,000 images for testing. So in the test set, there is 2 new unseen authentic sources and 6 GANs. That's kind of described here again in a little bit more detail. We see that the Celeb HQ has 30,000 real faces, Flickr Faces has 70,000, so we have 100,000 authentic images in our test set, all of which are unseen during training and validation. And then we have 600,000 synthetically generated identities from 6 different GANs, 5 of which are completely unseen during training, and 1 of which is part of the training set, but completely different images, of course. That would be totally unfair if they were the same ones. And the way we want to evaluate this to actually truly understand what's going on here is using 4 out-of-the-box network architectures. So we use DenseNet, which is densely convoluted neural network, densely connected. We use ResNet, we use Google's Inception v3, and we use ExceptionNet, which is a variation to the Inception v3 network. So the idea here is if we train 4 different architectures in the exact same way with the classification loss, and then also with CYBORG loss, we can determine that any observed performance differences can be attributed to the CYBORG loss and not to something that's architecture specific, i.e. it's not just something going on in the DenseNet network that makes it look better. It's actually something that's helping the network learn across 4 different networks. So it's the observations then are not architecture specific. They're actually a direct result of the addition of the human saliency component of the loss. So all of them are trained at the exact same training procedure, same training data, same validation data, and they're all tested on the exact same testing data. The only difference is the architecture. Additionally, to go kind of one step further on that, what we decided to do is get a published work, the reference number 4 here, which was developed for synthetic face detection. We take that and we just simply take their original implementation and replace the loss function from their work with CYBORG. So we train their original implementation on our data, and then we train their original implementation, but replace the loss function from the original implementation with CYBORG and train on the same data again. And this is basically to try to show the versatility of CYBORG in that it can be just implanted into current methodologies. And finally, more so as like an exploratory kind of experiment here, this is not to do with CYBORG. We take a self-attention approach where generally in self-attention you have a mask which defines regions of tampering or something to do with the task, and you're trying to get the network to be attentive to this mask. And in general, they're quite coarse. Say for a face, it would just be the mask of the face, something like that. So what we want to do is just simply replace the traditional attention maps with human saliency maps to see if these human saliency maps can be useful in this application. So this isn't a test of CYBORG, but it's more of a viability test of these human saliency maps. How useful actually are they outside of this CYBORG loss? So now I will talk briefly about, or I'll talk about the results, but briefly, this is one of the results that we saw first during training, and that is protection against overfitting. So this is a nice thing to do with that we see in deep learning. We see a lot of overfitting to our training data in deep learning, especially in limited data scenarios. Models tend to quickly learn something about the training data, but unfortunately, in a lot of cases, even though the data looks semantically similar, we see that it just doesn't do well on either validation or test data. So what this graph is basically showing here is the validation accuracy and training accuracy as the training progressed. So on the x-axis, we have the current epoch, on the y-axis, the accuracy. So the first thing to note is the brown dotted lines and the purple dotted lines, which correspond to the training accuracies. So in both cases, we see that after about 10 or 15 epochs, both cases, the training accuracy goes to about 100%. So it's clearly learning something important, something representative of the training data, such that after about 15, 16 epochs, it can now classify the training data at almost 100%. However, now when we look at the validation accuracies, this blue line corresponds to the experiment with just classification loss alone. And this orange line corresponds to the same training procedure, but with CYBORG instead of just classification loss alone. And what we see is something quite significant in that for the classification loss alone, the validation accuracy is a kind of roughly around 85% for the duration of training. However, for the CYBORG models, also important note here, side note, this is for 10 models. We train 10 models in the exact same way. And the shaded regions that we see here is plus or minus 1 standard deviation. So this isn't just one single model. This is a aggregation of 10 trainings. So we wanted to make sure that the observations were significant and statistically significant. So going back, we see that for the CYBORG models, the validation accuracy is over 90%. So over a 10% increase in validation accuracy just by adding these, just by adding the human saliency component. So basically this is telling us that adding this CYBORG to the network is letting the network learn something that is a bit more generalized to the validation set rather than just training with classification loss alone. Moving on from that, now we're looking at the test sets, and we see that for both, for the first two out-of-the-box networks, DenseNet and ResNet, the blue line, again, this is for the 10 models that we saw before. The blue line corresponds to classification loss alone. The orange line corresponds to the same images as the blue line, but with CYBORG loss instead of classification loss. And then the green line corresponds to the 7 times larger data set. And what we see in both cases here is that with the addition of CYBORG, keep in mind the blue line and the orange line use the exact same training images, with the only difference is we're adding the human saliency. We see an increase in DenseNet from 0.511 to 0.633. And in the case of ResNet, it goes from 0.537 to 0.612. So that's a significant jump in performance for both of these networks. Additionally, when you train on classification loss alone, but with 7 times the data, it does not perform better than with CYBORG. We see that the AUC is 0.594 in this case, and 0.585 in this case. So even with 7 times the data for these two networks, the performance is not greater than adding CYBORG. For this next two networks, for inception and exception, we see something a little bit different, but equally as interesting. What we see is that for the, again, in both cases, the difference between the classification loss only and CYBORG is significantly different. In both cases, we see an increase in performance by the addition of CYBORG. But for these networks, they seem to, with the 7 times the data set, they seem to completely overfit to this. And note that the 7x data set is from the same sources as the training and validation. So the performance on the training on 7 times data for these two networks is actually worse. Whereas when we take the blue line here and add CYBORG, the performance gets better. So actually, in some cases, adding more data is not the solution. In fact, we have to be smarter with the data. And this is one approach of doing that by adding human saliency, human in the loop type approach to it. For the fifth network that we trained, which was taking the already published method and replacing the loss with CYBORG, we see again that CYBORG can be directly added to a published method and a performance increase can be noted. Whereas the original implementation gets an AUC, all of these are on the same test set, keep in mind, of 0.554. When we add CYBORG instead of the traditional loss from that work, the performance goes to 0.591. Additionally, in this case, the 7 times data set was not enough to beat CYBORG as in previous examples. So the CYBORG approach actually gives us a greater increase than increasing the data set by 7 times. And the final experiment is the self-attention approach. So in this case, CYBORG is not used, but as I said before, we applied the human saliency maps to a self-attention mechanism, where we replaced the attention maps with human saliency. And in this case, we can see that the original implementation gets an AUC of 0.428. But when we replace these maps with human saliency, the performance increases to 0.498. Additionally, when you apply the same 7x data set to this self-attention approach, the performance is on par with CYBORG. So what we can see here is that, yes, there is a slight increase in performance when we add the human saliency to self-attention. However, the performance increase in self-attention is not as big, it's not as significant as when we use these human saliency maps in the CYBORG loss function instead. So although they are useful in self-attention, they're not as useful as when you train using CYBORG. So in conclusion, kind of as a summary of what I've just talked about, the first thing that we found in this paper is that the addition of forced annotation to human data collection increased human subject performance significantly. We saw the median pair accuracy go from 50% to nearly 70%, almost a 20% increase. Additionally, we also saw that in all of our experiments, the addition of CYBORG resulted in a significant increase in performance on the test set. We say that this test set is unseen data and it's a pseudo open set type approach because 5 out of the 6 GANs in the test set, so 500,000 of the images, were from completely unseen architectures. So this is assessing the generalization capability increase that we see by adding CYBORG. One of the most interesting things, I think, is that the value that we can add to our data using this approach. We saw that using CYBORG resulted in a greater performance increase than increasing the data set time 7 times. We would love to go to 8, 9, 10 times, keep going until it beats it. But unfortunately, we ran out of live training data. So we couldn't go beyond 7x, unfortunately. However, the key thing to take away here is we can add significant value to our limited data by adding human saliency to the training procedure. So in cases, in a lot of times, how do we get more performance? A lot of people will tell you to just add more data. And especially in deep learning communities, data is the key. We want to just keep adding data until we get the state of the art. But we propose that you can get greater performances than just adding data by adding value to the limited data that you have through human saliency. And in cases where you can't just get more data, like in synthetic face, where you can just generate more, say in this case, you can just generate more synthetic face for training. However, say in fraud detection or medical imaging, or cases where there only is a limited amount of data, you can't just generate more data, especially in medical imaging or something like that. We can add more value to that data. We can get the most out of that data using human saliency. We also saw that there was a regularizer effect from this, in that it was a protection against overfitting that we observed. So this is a good thing for the deep learning community as well, because we want to be sure that our models are learning something that we can kind of interpret. So if we know that we're guiding it towards human saliency, and we know that that's helping against overfitting, then we can make an assumption there that the features that it's learning, whatever we're guiding it towards, is more useful and generalized, like a human would kind of classify things. We also see that when we apply CYBORG to a tradition or an already published method, by just implanting it into an already published method, there is an increase in performance, as I've shown in the previous slides. And finally, when you use these human saliency maps in self-attention, there is a performance increase, but it's not as great as if you use these human saliency maps in the CYBORG loss. Use CYBORG loss in your training procedures. So that's basically the main conclusions of our work. The study, with a lot more technical details, i.e. how we generate the class activation maps for each batch, as well as a little bit more in the weeds stuff about how we implemented it, can be found in our paper, which is now on arXiv. And additionally, I'm planning to release the data soon, as well as the code. So I'm really excited for people to have a look and try to use it themselves and potentially make it better, because I'm sure there is much more cool ideas than what we currently have. And I really want to see what you guys can do with it. So yeah, I really encourage you guys to read it and ask me any questions. I'm always available via email, which can be found on the paper. And additionally, if you have any questions today, I'm going to be here to answer it, as well as my advisors, Dr. Bowyer and Dr. Czajka, who will be able to answer questions too. But if you have any questions for me, I'd love to hear them. This is a new area that we've kind of started working in, and I'm super excited by it. The final word, we'd like to thank our sponsor, which is the US Department of Defense, and our colleagues down in Crane, Indiana, have been helping us greatly. They've been so active in helping us with this work, and we thank them so much. They've just been so awesome in helping this work get to the position that it's in now. And we're just super excited to continue working with them into the future and coming up with more cool ideas like this one. So thank you. I hope you had a great day attending the CVRL tutorial. I know the other presentations were amazing. I'd like to thank again Dr. Bowyer, Dr. Moreira, and Dr. Czajka, as well as Patrick Dinsey, one of my co-authors, for all of the work that they've done and all the help that they've given me throughout the way. And again, I'm open here for questions, either today at the conference or in future on email. So thank you, and thanks for listening to this.